What is beyond the edge of the universe? For thousands of years, humanity has looked to the stars and wondered where they fit in the universe. It's not like the interest in what lies beyond Earth is anything new. From planetary theory in ancient Mesopotamia to the Mayans coinciding their cities with astronomical events, humanity has placed great interest in the unknowns that lie beyond Earth. The universe is incredibly vast, and naturally, humans always wanted a glimpse beyond its limits. To answer the question of what is beyond the universe, we must first understand what the universe is. So join us on a journey as we explore the mystery of the universe and ponder its future. We'll travel back to the dawn of the universe, witness its evolution, and gaze into the distant future. We will seek the boundary of the cosmos and question if there is truly an edge to what we know. But before we dive deeper, click on the subscribe button and don't forget to turn on your notification bell so you don't miss out on any of our videos. First, let's talk about what the universe is. Then we can speculate about the beyond. Imagine the universe as everything we can see and measure using light. That's called the observable universe. But there's a catch. Anything farther away than the light has had time to reach us is like a mystery because we can't see it. It's all dark out there. The problem with this is that it's not a technical limitation. It's not that we're not advanced enough with our technology to peek behind that mysterious veil. It's simply a limitation due to the speed of light itself. In the same way, you can't read a letter that hasn't arrived yet. The universe itself is expanding at an increasing rate, which means that the mysterious border is moving further away from us. A radio signal from Earth would technically never be able to reach the edge, even if it traveled toward the edge for an infinite amount of time. Light travels at a speed of approximately 300 million meters per second. So when something is close, we see it almost instantly. Like if you're looking at a car across the street, the time it takes for light to travel from the car to your eyes is practically zero. But here's the catch. If you stare at the sun, you're seeing it as it was 8 minutes ago. That's because it takes about 8 minutes for light to travel from the sun to Earth. So what you see depends on how far away it is, how long it takes for light to get to you, and how fast light travels. Scientists who study the universe have tried to understand what's beyond what we can see. The universe doesn't stop where we can see it, it goes on beyond what we call the cosmic horizon. Just like the ocean continues beyond the horizon at the beach. The limit of observability in the universe is set by cosmological horizons, which limit, based on various physical constraints, the extent to which information can be obtained about various events in the universe. One famous one is the particle horizon, which is the farthest distance we can see because of the age of the universe. It's like a boundary between the observable and the unobservable regions of the universe. Then there's the Hubble horizon, which separates things moving faster or slower than light relative to an observer. Note that this does not mean the particle is unobservable. The light from the past is reaching and will continue to reach the observer for a while. Also, more importantly, in the current expansion models, light emitted from the Hubble radius will reach us in a finite amount of time. Now let's turn the cosmic clock backward and explore the cosmic countdown leading up to the Big Bang. We'll navigate through a timeline where the building blocks of our reality are being assembled. From the tiniest particles to the emergence of fundamental forces, this is the cosmic overture setting the stage for the main event. The Big Bang marks the moment when the universe erupted into existence. But what exactly happened during this mind-blowing event? Picture an infinitesimally small and dense point, a cosmic seed that contains all the energy and matter of the universe. Suddenly, it expanded rapidly, giving birth to space, time, and everything in between. Galaxies, stars, and planets burst forth, painting the cosmic canvas with the colors of creation. As our universe was born, it didn't sit still. Instead, it embarked on a relentless journey of expansion. Imagine galaxies as race participants, each sprinting away from the starting line. This ongoing cosmic marathon shapes the very fabric of space-time, creating the vast and ever-growing universe we observe today. Hold on tight as we ride the cosmic wave of expansion together. The expansion of the universe was figured out by using both ideas from physics and observations made by astronomers. But sometimes they can't directly see things, like with gravitational waves linked to the Big Bang's leftover radiation. In 2014, scientists thought they found these waves, but later they realized it might just be dust in our own Milky Way. The journey to understanding the fate of the universe starts with Albert Einstein. Einstein believed that gravity would work against the commonly understood idea of a static universe that was widely accepted in his time. He thought that the gravitational force would cause things to contract. However, this was not happening. Einstein concluded that there must be some repulsive force to oppose this, which he dubbed the cosmological constant. However, in 1929, Edward Hubble discovered that a galaxy's redshift is proportional to its distance. Applying the concepts of general relativity, this was thought of as the fabric of space and time expanding. This new information implied an expanding universe, and so Einstein discarded his work with the cosmological constant, though this is not the last we'll hear of it. In 1964, Arno Penzias and Robert Woodrow Wilson were trying to detect radio wave echoes with a super-sensitive antenna. The antenna persistently detected a low, steady, mysterious noise in the microwave region that was evenly spread over the sky and was present day and night. At the same time, another team, Robert H. Dick, Jim Peebles, and David Wilkinson, were attempting to detect low-level noise that might be left over from the Big Bang and could prove whether the Big Bang theory was correct. After the Big Bang, the universe kept growing, but slower. As space got bigger, the universe cooled down and stuff started to form. Just 1 second after the Big Bang, the universe was filled with different particles like neutrons, protons, electrons, anti-electrons, photons, and neutrinos. During the first 3 minutes of the universe, the light elements were born during a process known as Big Bang nucleosynthesis. Temperatures cooled from 100 million, which translates to 1032 Kelvin, to 1 billion, which is 109 Kelvin, and protons and neutrons collided to make deuterium, an isotope of hydrogen. Most of the deuterium combined to make helium, and trace amounts of lithium were also generated. For the first 380,000 years or so, the universe was essentially too hot for light to shine. According to France's National Center of Space Research, the heat of creation smashed atoms together with enough force to break them up into dense plasma, an opaque soup of protons, neutrons, and electrons that scattered like the fog. Roughly 380,000 years after the Big Bang, matter cooled enough for atoms to form during an era of recombination, resulting in a transparent, electrically neutral gas. This set loose the initial flash of light created during the Big Bang, which is detectable today as cosmic microwave background radiation. However, after this point, the universe was plunged into darkness, since no stars or any other bright objects had formed yet. About 400 million years after the Big Bang, the universe began to emerge from the cosmic dark ages during the epoch of reionization. During this time, which lasted more than 500 million years, clumps of gas collapsed enough to form the first stars and galaxies, whose energetic ultraviolet light ionized and destroyed most of the neutral hydrogen. Now that we know the universe is expanding, we begin to gain a little insight into how the universe might end. With this expansion occurring, the galaxies are moving increasingly farther away from each other. As time continues for billions of years, things will begin to cool down. By this I mean stars burn out, and the ingredients needed to form new stars disperse to the point where star formation ceases. All the lights fade and the night sky goes dark, and the day sky for that matter. There's nothing left to occur in the universe as it approaches minimum temperature and maximum entropy. A stable state of low dissipated energy is reached. Of course, this implies systems will not have enough energy to produce mechanical work. This scenario is referred to as heat death. Fast forward to 1998 when the Hubble telescope discovered that the universe used to be accelerating at a slower rate. This new insight was achieved by looking at the brightnesses from distant and old supernovae. So now the universe is expanding at a greater rate. Okay, but how? If gravity pulls in, what is causing things to be pushed away? Not only this, but how are things being pushed away faster and faster? The answer is dark energy. Dark energy is thought to make up about 70% of the universe and is theorized to be an intrinsic property of space. This new data suggests that Einstein's cosmological constant idea was very close. Unfortunately, there is still very little known about dark energy, as it is not directly observable. The math that proves its existence implies that as space expands from the forces of dark energy, there becomes more space further driving the spread of galaxies. The effects of dark energy add up over these vast spans of emptiness, causing the universe to expand at faster and faster rates. The theory supported by this phenomenon proposes that if the density of dark energy becomes great enough, this acceleration will continue to increase until solar systems, planets, atoms, and even quarks are ripped apart by dark energy. In the case of indefinitely continuing cosmic expansion, the energy density in the universe will decrease until, after an estimated time of 101,000 years, it reaches thermodynamic equilibrium, and no more structure will be possible. This will happen only after an extremely long time because first, some matter will collapse into black holes, which will then evaporate extremely slowly via Hawking radiation. The universe in this scenario will cease to be able to support life much earlier than this, after some 1,014 years or so, when star formation ceases, until quite literally the fabric of space-time itself tears. This is known as the Big Rip. What do you think? Let us know in the comments section below, and don't forget to like and subscribe to our channel for more updates.